In this tutorial, we will make a start on doing register-level programming on the ARM microcontroller. Register-level programming, also known as bare metal programming, allows the programmer much more precise control over the microcontroller's features and peripherals. I'll be using the STM32F discovery board for this example. I'm going to implement a piece of simple software to flash one of the onboard LEDs on and off at a regular interval. This should enable us to generate a basic idea of how to do register-level programming on the microcontroller using the masking techniques which we covered in previous tutorials. When you open the Keil software for the first time, you will see the main console window which is shown here. If this is the first time you're using the Keil software, you will need to install the relevant packs for your device. This can be done by clicking on the button here. When the menu opens up, find your device in the list. If the device you're using doesn't appear in the list, then refresh the page using the button at the top. The refresh process can take a very long time, several tens of minutes. While refreshing, some of the pack downloads may fail. If this happens, simply skip over them, as there is a high chance that they are not relevant to our application. Once the list has refreshed, your device should appear in the menu. Install the DFP packs and any packs that relate to the CMSIS. While these packs install, there may be some permission prompts. Simply click yes to these. And once all installations are finished, the packs that you have selected should show as installed, or up to date, or completed. We can now close the pack installer window. We can return to this window at any time in the future by clicking on the button. This will allow us to install additional drivers and packs for other devices in the future. To create a new project in Keil, go to the project menu and select New Project. The project will consist of many files, and so should all be contained inside a specially named directory. In this case, I have already generated an example directory called test, so I will simply give my project a name and click OK. I will select the device I'm using from the menu and include the necessary startup code files. This requires the core and system init files. These files are dependent on each other in order to work. If you include a file without including one of its dependencies, it will show as orange to flag a warning, and it would also show you down at the bottom which file is missing. When everything is happy, it shows as green, so you may proceed. Now I have generated my Keil project. The two files which I included at the end are listed here. The startup.s file contains the code which is run as soon as the microcontroller is powered on or released from reset. It contains assembly instructions which handle the startup procedure. After a reset, the code begins to execute from the reset handler vector address which is shown here. The first thing it does is jump into a function called system init, which is contained inside the other file which I included. This then goes on to call further functions which set all of the register addresses to their default values. After all this initialization has completed, the setup routine then calls a function called main. This is what will contain the user-defined code, and is what I am now going to write. In my project tree, there is a folder called source group 1, which is where all of my source codes will be contained. I can create a new source code file by right-clicking and selecting Add New Item to the group. This file will be a simple C file, so I select that from the options list, and I give it a name. Seeing as this source page will contain my main function, I will simply call it main. Now that I have created this source file, it appears inside my source group folder. This is a blank source code sheet where I will begin to write my user-defined code. Before anything else, I need to include the relevant header file, which will import all of the relevant definitions for this device, such as register addresses and masks. I will then create a function called main, like this. The user-defined code must consist of a function labeled main, which matches the format specified in the startup file. Without this function, the user-defined code will not run. When the microcontroller begins to execute code within the main function, it will start at the top and work its way down through the successive instructions. It must not be allowed to reach the end of the main function. If it does so, the microcontroller will go into either a reset or an error. To prevent this from happening, a while loop is put in place, like so. A while loop will continue to loop as long as the condition within the parentheses is met. In this case, I have simply put a 1, which means that the condition will always be met, regardless of all other activity. Text contained within this source file will be treated as instructions. It is possible to place comments in the code in order to explain what's going on. Preceding a line of text with 2 forward slashes like this will turn it into a comment, which means that this text will not be treated as an instruction and will be ignored when the code is compiled. Any code placed before the while one loop will only run once on startup. This is where any initialization code should be placed. Any code contained within the while one loop will run continuously. This is where code that runs the main program should be placed. ARM development boards come in all shapes and sizes, but they all consist of the same basic hardware. They have the main microcontroller and the USB interface chip, which translates the USB data onto the microcontroller for debugging and programming. The board is powered from the USB and automatically enumerates with the PC when the USB cable is plugged in. On the PC, you can go to Device Manager to check if the board has been recognised. If this is the first time you've used Keil on this computer, the chances are the USB drivers have not yet been installed, and the device shows with a warning. To install the USB drivers, go to the directory as shown, and install the 64 or 32-bit USB driver package, depending on your operating system. Once this completes, the correct drivers will be installed, and the board is ready for use.